That is to look a bit more on the R thing. We already started it. Let me just check. I didn't collect any interesting data today, but let's have a look at today's data anyway. What is the mood situation? It's not too bad, actually. Changing rapidly now. We have a group of like 18 people hooked up, not in the building. Anyway, let's go into R again as the final part. I already showed you this basic use of the debinome and the p-binome function. Actually, it's quite easy to use the bar plotting, like this. There is a bar plot function just to show you how it's nice to illustrate different distributions. Here I'm looking at the probabilities of the binomial. I'm looking at a binomial with like 10 rows with a coin. I am first of all looking at the 50-50 binomial, so the completely symmetric. I am trying to look at what are the probabilities for all possible outcomes, 0 up to 10. And then I'm doing a plotting of those. And here they are. Here are the distribution. Here's the 50-50 binomial distribution with 10 rows. What if it's not symmetric? If the underlying probability is 0.8, now here's the distribution. What if I plot, I could also plot the p-binome here, the accumulated probabilities. And I hope not surprisingly, I made an error. Not surprisingly, it is when you add up the probabilities, they start at 0 and they add up to 1. So this is an example. If you bar plot another one, if you bar plot the 0.1 thing here, it'll add up much previously. If we plot the 0.8, it will add up later on. But finally, it will add up to 1. Right? But there are different binomial distributions depending on p. Actually, here's just a reminder that the choose function, that's a binomial coefficient, which is directly in R. And the factorial function is also in R. Here's like choose, I think, 5 out of 10. Choose 5 out of 10. Choose maybe 10.5. Yes? Choose 5 out of 10. Anyway, if you're confused about the options, you can always write question mark to a function, question mark choose, and you get maybe a boring, but if you want to check, you get a description of the function with examples and options and everything. So you can do that to all functions in R. I want to show you one more thing that will be important in our course, but now just a teaser for today. There are other functions then. Let me just show you on the slide. Here's the single slide I have on the R today. There are a number of generic functions where we already met the D and the P. We met it for binom, we met it for poise. It's also there for the hypergeometric, but I didn't bother telling you all the options there. But it's there, of course. Then there are two others. There's the Q and the R. Q is for quantile, percentile. Maybe even the better word related to what we have learned last time. That's the inverse of the P function. We get back to that, but actually our percentile thinking from last time, that's actually the inverse of a probability function. That's where you're given a probability, you find the point that matches the probability, right? Rather than given a point, you find the probability. So Q is exactly, mathematically speaking, the inverse function of the P function. Then the one I was going to mention now. This is actually a major mistake that I'm going to change as rapidly as I come back due to something in the back old time. It's definitely a part of the syllabus, so it will be changed when I come back to my chair. It is definitely a part of the syllabus. The nice thing is that we can make, talking about the randomness discussion that I started out with, and the lotto and the game stories, we can actually make the computer do random things for us. Not really, but intelligent people made things for us such that we can do as if. So we can, for instance, say our binom, 1/150. That is like, let me do like this. Let me do like this. It's a bit, but now I'm randomly throwing a coin here on my computer. Sometimes it's a 0, sometimes it's a 1, right? It's a bit tedious. If I wanted to throw more coins, it's R for random. I could just say, I want to throw, no, I should do like this. I want to see, N should be 100, P should be 0.5. I want to simulate, I want to take one random binomial out of, sometimes it's 52, sometimes it's 56, sometimes it's that. I could actually also, if I wanted to, easily make 100 of such, right? Whoop. The nice thing about making 100 would be I could also easily make 1 million, actually. It's very rapidly done. Then I could take what is the variance of, let me do a simpler one. What is the mean of these 1 million outcomes? It's 50, funny enough. I've actually computed the mean of 10,000 random binomials on my. I did 10,000 times. I threw 100 coins here in a split second. I hope you get the feeling of the perspectives of this. How easily you on the computer can simulate and compute systems, outcomes of systems that are very, very, very complex. Simulation methods that I've just teased you with here are going to be important in our course, and they are extremely important out there, not only for statistics, but for modeling, and in any case. Okay, that's it for today. Next time, we're up with Chapter 5 on continuous distributions. I really sincerely hope that all the quiz things, maybe we're not 100% there, but I know my computer guy, Philip, you have seen his name now. Too bad for Philip. He didn't sleep much the last few days, so I hope we are closer to everything working out. Please report any bugs still to Philip. That's the best way of finding out how to clear the bugs. Have a nice day out there, and see you next week.